All right, here we are again with another lab. This time it's thermodynamics. Thermo means temperature, heat. Dynamics means movement, not static. Thermodynamics, movement of heat. And that's really where the basis of thermodynamics came from, was heat is energy which flows, and therefore they study the flow of energy. And it's something that we're going to do with this lab. What we're going to do in this lab is basically we're dealing with being able to predict a precipitant when two reagents are mixed based on the thermodynamic equations. And we know that if Gibbs Free Energy is negative, then a reaction will spontaneously flow in the direction in which it is written. So what we're going to do is we're going to figure out the Gibbs Free Energy change for a reaction. And based on the sign on the Gibbs Free Energy, we'll know whether that reaction will flow in that direction spontaneously. The reactions we're going to talk about are going to be precipitation reactions. And therefore, to get the proper equation, they must be written as a precipitation. For instance, if I have lead 2 plus 2 I minuses, they would go to give me PbI2 solid. That would be written as a precipitation. Dissolving KSP that we just did, that would be written the other way around. But because we're dealing with precipitation reactions, we must write them in the correct direction. There's a lot of very specific things you have to do to get the right answer for this lab. And then it comes down to just a series of calculations. But I want you to kind of get an idea of the overall for what we're doing with the lab. So then what we're going to do is we're going to be able to base it on the fact that this is equal to the Gibbs free energy of standard state for the reaction. Standard state means 1 molar, 1 atmosphere of pressure, it's at 25 degrees Celsius and blah, 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 standards. But we're not going to be doing that at standard state conditions. So we have to do an additional calculation to get it from standard state conditions, and that is plus RT, R being what? R is the gas constant, but it's used in a lot of calculations, and there's a very specific one we're going to use, and for this lab we're going to use 8.3145 times 10 to the negative 3 kilojoules per mole. We want to do it in kilojoules per mole because that'll give us the right answer. And then we're also going to always do these things at 298.15 Kelvin. So first thing you might want to do is calculate those two together, because that's a value we're going to use all the time, because it's going to be RT, and then it's basically RT, the natural log. So I'll write ln Q. And what's Q? Q is our mass action equation. That is, it's products over reactants raised to the coefficient from the balanced chemical equation. But not, and it comes from this balanced chemical equation, okay? That's the coefficients from this, the precipitation balanced chemical equation. You'll see why I'm saying that and why it's so important in a little bit. So let's figure out what this value is just so we have it. 8.3145 e to the negative 3 times 298.15. So that gives us a value of 2478. Let's carry an extra guard digit, 97. That's the value we get, and that's going to be joules per mole. I believe that RT is joules per mole Kelvin times Kelvin. So that's going to be this value in kilojoules per mole. So 2.47897 kilojoules per mole. We're going to use that value. I'm going to write it down. I'm going to keep it on this separate piece of paper. All right, let's go through and talk about how we do these calculations. Again, there's 4 separate steps to this, and I know you're going to want to take a shortcut and bypass it, but if you do, there's like a 99% probability you'll get the wrong answer, because I've seen this, I've been doing this for a lot of years, and I see it happen all the time. So the easiest thing to do is do this in the 4 steps, because there's a lot of different parts to this that makes it seem like it's really simple, but it really isn't. So first and foremost, what are we going to be looking at? We're going to be looking at a reaction that is in 0.2 molar of lead to nitrate. That's PbNO3 2. And then it's going to be mixed with a solution that's 0.20 molar. This is the same way it's going to be on the calculations you're going to do. 0.2 molar is the molarity of the solutions that we're going to start with. And that's going to be magnesium iodide. That's MgI2. Okay? And these are both in solution, and the two solutions are mixed. So now we're going to mix the two solutions, and we're going to use our ultimate equation is for Pb2 plus, well, what's the first thing we need to do? I'm already doing it. I need to talk about it. First thing we need to do is, well, what are the possible precipitants that could come from the mixture of these two solutions? Well, when you're trying to figure out what possible precipitants there might be, what you do is you have to have a cation and an anion come together and have a greater affinity for each other than they do for water, and then they'll come together, lose their charge, no hydrogen bonding, they fall out of solution. Well, we know it's not lead nitrate because that's already in our solution over here. We know it's not magnesium iodide because we already have those ions in our solution to begin with, so they had to dissolve. So the only possibility are lead iodide and magnesium nitrate. So those are the two compounds we're going to be looking at. For your handout, I've already put in the list of possible precipitants that you will be investigating because I want you to do them in that way. I'll show you when we get to the end here. So one of the things we have to do is we have to figure out what is the concentration of these items in solution. We know it's 0.20 molar in lead nitrate and 0.2 molar in magnesium iodide, but we know that, and this is dissolving, not precipitating, because at first these go into solutions. We had to figure out what the molarity of the individual ions are. We have PbNO3 2, and that's going to go into solution as Pb2 plus 2 NO3 minus. And we have magnesium iodide, and that's going to go into solution as Mg when it was dissolved as Mg2 plus 2 times I minus. Okay? So if it's 0.2 molar in this, what is the molarity of the lead? Our Pb2 plus must be 0.20 molar. Why? Because for every mole of this that dissolves, 1 mole of this is formed. But what must be our concentration of nitrate? Our nitrate concentration must be NO3 minus must be equal to 2 times 0.02, so 0.40 molar. For our magnesium, again, 1 to 1, so our magnesium 2 plus must be 0.20 molar. But our iodide, again, is equal to 0.40 molar, okay? So that's the actual molarity of the ions when they're in solution, okay? That's step one. Step one is figuring out what the molarity of these things are in the solution before they're mixed. This is the actual solutions we pick up. It says it's 0.2 molar in this, but that means it's 0.2 molar in lead 2 plus and 0.4 molar in nitrates. And then we say the same thing here, but then we mix the solutions, and ultimately we're looking for a precipitation reaction. Let's do the first one. The first one will be lead 2 plus 2I minus goes to give us PbI2 solid. That is our precipitation reaction. PPT is the way they typically give for precipitation reaction. That's the reaction we're going to base our Gibbs Free Energy calculation on, okay? It's going to be based on this. So this is what we're going to use for that. So before that, we need to figure out what the standard state is. What is the delta G naught for this reaction? Well, delta G naught is final minus initial, right? It's change in energy. It's change in Gibbs free energy is equal to the change in energy. That's final minus initial. Final minus initial. Well, final is lead iodide. Initial was lead 2 plus and 2 iodide. All of these require certain energies to form them. And in the handout, I believe that I've given you those values for that. So in this case, you don't have to look them up. We'll go through how you look them up to do the lab. But for our case, we've already got those. And that is, the handout tells us that the Gibbs free energy of formation of lead iodide is negative 173.60 kilojoules per mole. So one thing about thermodynamics, sign is everything. You must keep track of negative signs. You really need to keep track of positive signs, but students never want to write down positive signs, but you must keep track of your signs. It's very, very important, okay? So we said it's change final minus initial, and then initially that's the lead 2 plus, And if we look it up, the Gibbs Free Energy for the lead is negative 24.40 kilojoules per mole. Plus, now I'm adding the negatives, but it's going to be the negative of a negative here. Also for the iodide, that's I2, but there's two of them, but we don't square it. That's different. That's for like formations and everything else. This is for the energy. There's two of them, so it's 2 times the energy of 1. And in this case, the energy of 1 is negative 51.57 kilojoules per mole. Okay? So all of that's important. We put the products minus the reactants, and the reactants are not raised to the coefficient from the balanced chemical equation, but they're multiplied by the coefficient from the precipitation reaction that we're dealing with, because we're trying to find the Gibbs Free Energy, standard state Gibbs Free Energy for this reaction as it's written, so it must be written as a precipitation reaction. I know it's a lot of things to keep straight, but I'm telling you, you got to take this slow and easy. And once you get in the handle of doing these calculations, you can do them a little bit quicker, but it's not going to be something you're going to be able to do very, very fast. You have to be slow, methodical, and careful. So if we add all that up, you should get equal to negative 46.06 kilojoules per mole. Okay? So that's for our Gibbs Free Energy. All right? Then, what's the next step? Well, the next step is we're going to mix together those two solutions. The two solutions, one has the lead at 0.2 molar, and it has iodide at 0.04 molar. But we're going to mix equal volumes of each. If I mix equal volumes of each, I'm going to double the volume, but I'm not doubling the ions, right? If I add some lead nitrate and some magnesium iodide, I'm going to double the volume of the solution, but I'm not doubling the lead because this doesn't have any lead in it. I'm not doubling the iodide because this doesn't have any iodide in it. Therefore, if I double the volume without doubling the ions, the moles stay the same, the liters doubles, even though it isn't liters, doesn't matter, volume doubles, the molarity goes to half. Therefore, when we mix the solution, what we're going to be dealing with is lead 2 plus is going to be equal to 0.10 molar, and our iodide is going to be equal to 0.20 molar, okay? You've got to do that. You've got to figure out what it initially is, and then it's going to be half of that when you get to doing your reaction, all right? That's very, very important to do that because that's the concentration after mixing, okay? This is before mixing. Okay, now we can go to our equation. And our equation says delta G of reaction is equal to delta G naught. I'll just write it out, then we'll put the values in of the reaction, plus RT, that's the value we already calculated out, ln of Q. Q is products over reactants from the balanced chemical equation. That's this, the equation of interest, the one we're working on. So that means delta G of reaction is going to be equal to, we figured it was negative 46.06 kilojoules per mole, plus, what was our LNRT? We said that was 2.47897 times our, times ln. And this is like all one thing. ln of Q. Well, Q is products over reactants. Well, the products are solid. Solid molarity does not change when volume changes, remember, because as the volume of a solid gets smaller, the number of moles gets smaller proportionally, and it doesn't change. So that's nothing. That's represented as 1. It doesn't change. Over top of our reactants, where our reactants are the iodide, and we said the iodide in the mixed solution was 0.2 molar, 0.20 molar, squared, because this is Q. It's like our equilibrium constant, which is what it is. So it gets the exponent from the coefficient of the balanced chemical equation. Again, the equation of interest, that is our reaction. Let me write this a little bit bigger and easier for you to see. So that's going to be 1 over 0.20 molar squared times times our lead. And our lead we decided was 0.10 molar. So that's our calculation. That's what we calculate out. So we calculate out, we get delta G of reaction should be equal to our negative 46.06 kilojoules per mole plus, well, let's calculate this out. So we've got, if I did it right, we've got, turn on, clear, 2.47897 times ln. Let me find where ln is on this calculator. I don't use this calculator that much. I can see log, there's ln. ln of, what is it going to be? It's going to be 1 over 0.2 squared, which is 0.04, times 0.01, which is 0.004, but I'll put it in here anyway. 0.2 squared times 0.1. And that gives me a value of 13.687. So 46.06 plus 13.687 gives me a final delta G of reaction equal to negative 32.37 kilojoules per mole. Now note one thing. When we just did the basic thing, it was negative 46. Is that a spontaneous reaction? Yes, it is. Negative value. And look, after dilution, it's still spontaneous, but there's not as much driving force. The delta G is now down to negative 32.37. Does that make sense? Sure, these were at 1 molar. This is now diluted down to 0.2 and 0.1 molar. So it's much more dilute, much less driving force for a precipitation reaction to happen. Okay? Does that make sense? That's the method that you have to use to be able to do it. So what was the other one? The other one was, let's get a new piece of paper here. The other one was a magnesium iodide. So we go through the same process over there. So we had MgI2, and it dissolves, and we decided that our Mg2 plus before mixing was 0.20 molar, and we decided that our iodide before mixing was 0.40 molar. This is before. So after mixing, our magnesium 2 plus is going to be equal to 0.10 molar, and our iodide is going to be equal to 0.20 molar. Same thing that happened with the other one. What's the precipitation reaction? Mg2 plus, in this case, it's going to be the nitrates, right? So we have to figure out what the nitrates were because we mixed, this is what it became, but we are going to mix it with the lead nitrate, and we said our lead 2 plus was equal to 0.10 molar after mixing, and our nitrates were equal to 0.20 molar after mixing. Since we took the lead iodide for the first one, we're going to do magnesium nitrate for this one. So it's magnesium plus 2 NO3 minus goes to give us MgNO3 2 solid. Maybe. Depends on what the Gibbs Free Energy is for this. So again, we figure it out based on our reaction. We figure out what delta G naught is. And if we look that up on the if we look it up on the values that were given inside there, our delta G naught is going to be, well, the value for the magnesium nitrate we're given is negative 197.55 kilojoules per mole minus, and then for the nitrates we're given negative, it's going to be 2 times negative 111.34 kilojoules per mole plus the magnesium we were given as negative 454.80 kilojoules per mole. But of course, we're subtracting these negatives, so that's going to actually be added to it. And our delta G naught for reaction we get is plus 479.93 kilojoules per mole. So that's not a spontaneous reaction at standard state conditions. Then we have to figure it out. Our delta G reaction is going to be plus 479.93 plus our 2.47897 ln of Q. And what's our Q? Our Q is products over reactants. Products are not included. Reactants, same thing. It's going to be 0.2 squared times 0.1. And if we put that all in our calculator and do all the calculations inside there for what we get, we should get a value of plus 493.62 kilojoules per mole. Definitely does not precipitate out. Diluting it makes it even less likely to precipitate out. That makes sense. This was what we have 479. Now it goes up to 493 because it's diluted, less likely to precipitate. All right, so that's what you're going to do in the lab. You've got to do those calculations in the way I showed you. You've got to figure out what is the molarity of the individual ions before mixing, what is their molarity after mixing, delta G naught, using the Q from the balanced chemical equation for precipitation. Okay, so how do we figure out those values? Well, I just want to make sure everybody's okay on that. When you look it up, if I want to find out the value of silver chloride, it's right here. The intersection of these two. The individuals are for the individual ion formation. The values at the intersection are for the formation of the compound. So even if it's barium chloride, it's BaCl2. But for that gives you the value for BaCl2. You don't multiply it twice this or anything else. These values and the intersections are for the formation of the compound. The values underneath them across are for the individual ions. That's where you're going to get your values for your products minus reactants. You will have to multiply the reactant values, like for the barium chloride, that would be 2 times this chloride value plus the barium. And of course, you would take this initially minus 2 times the chloride times, but you do that. So like I said, in the table, you'll see that it has lists of the compounds, and then it has lists of possible precipitants that you're analyzing. I've already filled in the possible precipitants for you. Do those across the table in that way. The first 2 tables are delta G naught. That's real simple. Easiest thing is to go through and calculate all those out. Then you have to do the 2 for the reaction after mixing and after dilution for the non-standard state. That's where you have to do these calculations, and you must do the calculations. You don't have to do them the way I showed you, but if you take it step by step the way I showed you, first figure out what is the concentration of the ions before mixing, what is the concentration of the ions after mixing, what is the delta G for the basic reaction, then what is the delta G naught, setting up my Q based on that precipitation reaction. You got to write it as a precipitation, not as a dissolving. You will get the right values if you do it systematically, step by step, and carefully. All right. So remember, this lab is due this Thursday because the next lab is going to be on Tuesday, which is the last day of classes. I'll have the video up probably tomorrow for that last Nernst equation lab. It's not going to be a tough lab. I'll make sure it's pretty simple and pretty straightforward. This one's not tough. It'll take you maybe an hour to do the calculations, but that's all. So that's not bad compared to normally the lab is 3 hours. But make sure you do this and make sure you get this in Thursday. I will send out another email reminding everybody of that when it comes time. But make sure you do that because we're almost at the end of the term. I mean, this is it. Okay, so I'll see you next week for the last lab. Actually, not even, well, it will be next week for the last lab we're going to do. And then, have fun, whatever you do next term. Have a good one.